Hello and welcome to the EMC Live webinar, Faster Terminal Antenna Design and Certification with SAR Screening. My name is Belinda Stachukevich and I'm editor of Interference Technology, the creator of EMC Live. EMC Live Design Bootcamp is a new one-day online event hosted by Interference Technology. Featuring practical information and topics, this event includes roundtables and webinars on everything EMC design related, and there's no cost to attend. This is our first webinar of the day. Join us for our other webinars today. If you want to ask questions throughout the day, you can use the Twitter hashtag EMCLive. This webinar is presented by Benoit Derat. Benoit received the electrical engineering degree from CEPELEC and the PhD degree in physics from the University of Paris. He served as an expert in antenna design, numerical modeling, and SAR measurement for SAGM models from 2002 to 2008. Since 2004, he has been continuously involved in the development of international SAR measurement standards as an active member of the IEC and IEEE SA. In 2010, Benoit founded ARTFi with the aim to deliver innovative solutions for more efficient compliance demonstration to the wireless industry. This webinar is sponsored by our platinum sponsor, ARTFi. ARTFi's main goal is to provide EMF measurement, instrumentation, and expertise to support the electronics and wireless industry in efficient delivering of innovative and regulatory compliant products. This webinar is one of many today. To check out our others, visit emclive2015.com. A recording of this webinar and downloadable PDFs will be available on our website shortly. This webinar will be interactive. You'll be able to ask questions and we encourage you to participate. Take a look at your GoToWebinar navigation pane, the box on the right-hand corner of your screen. If at any time you have a question, we ask you to fill up the type box and hit send. To make the screen minimize and maximize, click the arrow button. To raise your hand to ask a question or report an issue, click the hand icon. We'll present the topic today for 35 minutes, followed by a 10-minute question and answer session. Now Benoit will begin the presentation.
Thank you very much, Belinda, for the introduction, and thank you very much, everyone, for attending. I'm very happy to be with you today, and I hope I will provide you very useful content for your activities. Just to introduce you a little more what we are doing at ARTFi, we are known for leading the second generation of SAR measurement system with the flagship product we have, the ARTMAN system, which takes accurate SAR measurement in seconds simultaneously for 1 gram and 10 gram. No robot is required with this system and there is no need to change the fluids. The way it works, all the phantoms you see on the top side of the ARTMAN system, the two heads and the flat phantom, they contain arrays of RF probes that are capable of measuring the amplitude and phase of the electric field, and then by means of advanced equations, let's say that calculate the Maxwell equation solutions into the phantoms, we can reconstruct the field in the whole volume. The ARTMAN is the first and only array system that's accepted by a notified body for certification testing to European regulations. Many labs and many mobile R&D departments already use it, and they receive quite a value in using it and accelerating their time to market. Okay, why we came up with this device, and in general, which is the topic of this webinar, is that clearly new technologies for wireless devices are making the SAR testing matrix larger and larger. If you remember, like 15 years ago or 20 years ago, the market of mobile phones was very simple with dual band handsets and not so many functionalities. These days, smartphones cover so many bands, like typically 5 times more bands than the dual band handset that we had back in time. Also, the advance in technologies like available LTE technologies, which brought up many good things in terms of data rate and application, made the SAR testing much more complex. In the past, we were used to have, let's say, a few frequency channels to test per bands and per mode, but these days with LTE, there is a need for testing different modulations, different bandwidth, different resource block allocations, so it's becoming a pretty large amount of testing per band. Also, in the recent wireless devices and antenna technologies that have been available, some new features have been used by designers, like dynamic antenna tuning, in order to adapt the tuning of the antenna to the presence of the user. In the same kind of idea, many wireless devices are also equipped with proximity sensors that sense the presence of the user and adapt eventually the power from the RF depending on the distance of the user to the mobile phone. The so-called ASDIV technology, antenna switch diversity. You may now have like two antennas for one transmission mode, used by the same RF front end, and they could switch during one transmission. And also simultaneous multi-frequency transmission like WLAN plus GSM together, and the MIMO technologies that are upcoming today. So this basically makes a lot more test conditions to go through when SAR testing a wireless device. Typically 5 times more band, 4 times more communication systems, and twice as many antennas as like 15 years ago. So it means like within these 15 years, there was a 40-fold increase in SAR test conditions. Well, this definitely makes the life of designers and wireless product manufacturers very difficult, because while this SAR test amount has increased 40-fold, the legacy SAR measurement systems definitely not evolved in terms of speed of testing in the same way. And they are based on the technology which is roughly from 20 years ago, using a robot system that moves a probe into the phantoms, and because of this mechanical movement, it typically takes about 20 minutes to get a SAR testing in one condition. Those legacy systems are definitely very slow and do not keep up, or too slow to keep up with new mobile designs and time to market constraints. The consequences are that antenna designers that may come up with very new ideas for new types of antennas that maybe would help having better radiation performances and better quality of the communication in general, sometimes may just not launch some of their designs because they are afraid that that could add some delays in the SAR testing, like some more weeks. And because of this, I would say in general, the whole world, not only the industry, but also the mobile consumers, would not benefit from potential innovations that are never released because of the fear of not, let's say, passing the bar of regulations. So definitely, these considerations were at the origin of a lot of effort put by the industry, standards committees, experts in SAR testing or in antenna design to define approaches to accelerate compliance demonstration protocols. There are several approaches to accelerate SAR testing for a mobile phone or a tablet or any kind of wireless device. One approach, which is a very natural one, is test reduction. It can also be very efficient. The idea behind test reduction is that based on some a priori information you may have on the device or on some of the modes that the device uses, you can decrease the number of test conditions. Like you think one condition will never be the highest SAR condition, and you can eliminate that. Of course, this needs very solid data to back up those kind of condition eliminations. The IEEE 1528 standard, the latest version from 2013, describes a number of procedures that apply within the scope of those test reductions. If I give one example, and we will give more detail about this example later, like for example, if you have one antenna that transmits in a given band that is shared by several transmission modes, like for example GSM and WCDMA at 850 megahertz, then in this condition you will have very similar SAR patterns, and only what will fluctuate is basically the power that's injected in the antenna for both of the modes. But it's very easy to analyze relatively the modes compared to the others and more or less try to eliminate the modes that have much lower forward power. Another interesting case is the case of actually most of the modern devices. Many of them, they have internal antennas that are built in the bottom of the device. And the SAR standards, they define two types of positions at the head, the so-called cheek and tilt position. The cheek basically reproduces the close contact of the phone when it's really held very close to the face of the user. But the tilt is a more loose position where the device would be tilted by 15 degrees and not touch the cheek completely. When you have the antenna built in the bottom of the device, clearly in a large majority of configurations, the close contact conditions, the cheek condition, will give a much higher SAR than the tilt condition. And we have other examples like this described in the standard. A more recent example also is actually the work that has been done within the IEC Standards Committee on LTE devices. There is a current standard document, a publicly available specification of drafting to allow reducing the amount of tests for LTE SAR testing. The idea of this draft is to reduce the SAR test condition based on conducted power assessment. What you can see here are some data that we measured with our system that basically show for a given phone different test positions at the flat phantom or at the SAM phantom, left or right, cheek or tilt, two different bands. And we measured many modes of LTE in those bands and in those positions, and we got the SAR values for all those modes, and we also got the conducted power. Each color relates to a certain position and band combination. And what you can see from here is that the SAR is basically linearly related to the conducted power, which is quite logical. You can see it's not perfectly proportional though. It's mostly because the conducted power testing conditions, especially in terms of loading, are different from the SAR testing conditions. But what you can see from this graph is that the low power modes are totally unlikely to be the highest SAR modes. So you can eliminate many of them. And actually, we evaluated that typically only the modes which are in the group of the 15% highest conducted power are the modes likely to deliver the highest SAR. Another kind of approach to fast-track the SAR testing is using fast SAR and screening approaches. Accelerating SAR by means of faster measurement methods is kind of also straightforward to understand. So the idea is if you have a faster SAR measurement system or tool or procedure, and you can apply it and basically measure all the conditions. So in this case, you don't reduce. And in the end, you will end up with a group of test conditions that give higher SAR. And you can reproduce those conditions with legacy systems to ensure the data you measured are solid, basically. IEEE 1528 2013 version also describes fast SAR screening procedure in clause 6.7, for example. And this fast SAR screening procedure is based on traditional hardware, so basically robot and diode detected probe. The idea is to measure less points in this case and apply different kind of processing to end up with faster with a SAR result. Also, the IEEE 1528 contains an annex, the Annex H, which extends the application of those fast SAR screening procedures to systems with different hardware, including array systems. There are limitations of classical fast SAR approaches. When I say classical, I think of using either legacy systems or amplitude-only measurement. When you use a robot system, it still takes about 5 minutes per test condition to get a SAR result. So it's 4 times faster than the so-called full SAR test, but still 5 minutes per test condition, when you get devices with 3,000 or 4,000 test conditions sometimes to go through, still makes a lot of time in terms of measurement, weeks of measurement. Also, another point is that fast SAR approaches based on amplitude-only measurement use rough a priori assumptions on field propagation. A very well-known approach is the Motorola FastSAR, which is basically describing the field propagation as having an exponential attenuation with depth into the phantoms, into the mannequin, which means that the field propagates as a single plane wave. It's definitely a very rough description of how the field actually behaves into the phantom. Diode-based arrays are not accurate systems, mostly because the probes in diode-based array systems are not that sensitive, and they have to be very close to the phantom surface in order to ensure that the application also of the Motorola FastSAR algorithm gives a reliable result, or other kind of approximations like that. So usually those systems, they use an array which is like within 3 or 4 millimeters to the phantom surface. And because of this, the array couples with the device under test and will change the behavior of the device under test. That's why actually it was decided to make a new standard, the 62209-3 standard, which is currently under work, which puts forward the concept of SAR 2.0, the second generation of SAR measurement, based on vector amplitude and phase measurement. It's a totally different concept, and it uses really the Maxwell equations to reconstruct the field inside the volume of the mannequins. It's not like classical systems where you assume no relationship between the points you measure. The physics actually say that there is a relationship between the different points, and this is taken into account in 62209-3. Well, basically the idea is that the Huygens principle says that if you measure a field in amplitude and phase over a surface, just two components, then you can get the 3D field assessment directly from the Maxwell equations. And you get the third component calculated from the two others using the Gauss relation. One of the very good things with those kind of techniques, which are kind of state-of-the-art actually in the near-field characterization of antennas that are more recent in SAR, in the SAR field, is that as you can use more sensitive probes and also you have amplitude and phase information, you don't need to probe the field in the region where you want the SAR. You can probe much further because the field actually, when measured in amplitude and phase, contains as much information, let's say at 20 millimeters, for example, from the phantom of the surface as compared to measured at 1 millimeter. So it's particularly suitable for accurate measurements with array-based systems. I can show one example of the accuracy of such systems that enter the scope of 62209-3. We made a benchmark with our system on 183 test conditions, 9 devices, 15 communication systems, 39 different frequencies, and we kind of tried every kind of positions on the three phantoms. What you can see on the graph here is the deviation of the 1 gram SAR in person compared to legacy system as a function of the 1 gram SAR value. And you can see that the very large majority of the points would agree within 30% with the legacy system, which by the way has a 30% K equal to uncertainty. Getting back to screening, and we made a kind of particular spot on arrays because screening is particularly useful when combined with the array systems. And you can reach very high efficiency gains in terms of mobile phone development, combining the two. I give here in this table an example of a tri-mode GSM, WCDMA, LTE handset, and for the sake of simplification, I only consider a case where we have a 4 head positions to go through. In such a case, if you have 3 modes and 4 head positions, you measure in middle channel, then you take the worst case position, and you measure in high and low frequency channel. You end up with basically an equivalent of 6 positions times 3 modes, makes typically 18 positions if you just have one band to test, or 18 tests, if you just have one band to test. Well, using a screening method, you would just screen through the modes for each position and frequency, and you would end up saving 12 measurements on the legacy system. And the table gives more details depending on whether the device uses antenna switch diversity, may use an antenna tuner with a number of states and different bands. And when you look at what you can save in terms of measurement on the legacy system, that takes typically 20 minutes per measurement, so you just take into account those 20 minutes, well, you can save up to 2 days on a multi-mode. On this simple case, up to 2 days of testing, up to 4 days of testing if you're using antenna switch diversity, or up to 16 days of testing with the device that's being tested as antenna tuner. And here, this is a really simple case that's limited to a number of test positions, and it's limited to a number of modes as well, transmission modes. Actually, the devices that are on the market currently, the 4G devices, they have many more modes and many more positions to be tested. So the gain here brought by a combo of screening and array system can be huge. In terms of regulatory acceptance for screening, well, as of today, the screening has been recognized by many important regulatory agencies. And let's say the traditional fast SAR approaches using the Motorola algorithm, for example, that already have a long history and their reliability is quite known in the field, are authorized by the FCC, Industry Canada, or also in Europe. As for probe array technology, the FCC has agreed to review SAR screening with Hartmann system for certification on a case-by-case basis. So I would say it's a first step. And in Europe, Hartmann is the only system that can be used for European DOC with respect to the RTTE directive. Industry Canada is currently running experiments on the Annex H of 1528 standard, and these experiments are made for testing the procedure, the screening procedure, when using array systems. And especially, they already tried on first generation of array system and obtained already good results. So now they want to extend the experiments on second generation array systems, and they are really, expecting a good outcome of this project. The Korean regulator, the RRA, already authorizes array systems for screening multiple transmission cases. How to use screening procedures for efficient and safe product design. By safe, I mean in terms of, for the manufacturer, not taking a risk to have a non-compliant product. Well, there is really one way that is very safe. There are many cases as of today in terms of test conditions where the SAR patterns are SAR distributions are extremely similar. Like communication systems transmitting at the same frequency, antenna tuner states well, antenna tuners are basically made for, let's say, compensating an impedance mismatch that's brought in by the user, by the proximity of the user. So they change the impedance, but they don't change the radiation properties of the device. And LTE modes within the same band, well, here the LTE modes may just, let's say, have some differences in terms of currents because they excite in a bandwidth that can be up to 20 megahertz, for example. They would excite slightly different frequencies, but 20 megahertz difference doesn't make much of a SAR distribution change. So basically what you would need for testing those modes with SAR patterns that are extremely similar, or rank them one compared to the other, is just a power meter that reproduces the head or body loading condition. That would be enough. The problem is that there is no power meter that can reproduce that other than a SAR system, because only the SAR system with the mannequin, the head or body mannequin, would load the device in the appropriate condition. But you can use an array system that will load the device in appropriate condition, and you will use it to basically monitor the power differences between the modes you're testing. Just giving you an example of similar pattern cases, this is one case we measured in our lab on a smartphone at SAM Lev Chick used at the frequency 1880 megahertz, and that's a frequency that's shared by GSM 1900 and WCDMA band 2. And actually, they look like a copy and paste, but they are not. Those two figures that are below and that are in the bottom of the slide, they represent the result of the SAR test, at least the distribution, for both of the modes, GSM and WCDMA, at the same frequency. You can see they are, if not identical, very close to identical. Another case is a smartphone that we tested recently in front position at 15 millimeter from the flat phantom. It was used in WCDMA band 8, each channel, and we just tested 3 tuner states. Again, you can see the pattern, they really look like copy and paste. And again, I promise you they are not. So, I mean, it's just really trivial science that the antenna tuner state will not change the SAR distribution. The key characteristics you need to check when using an array system or any other kind of fast SAR system to ensure that it's good enough for screening those kind of modes with similar patterns. Of course, it first has to be repeatable. That's a very important feature, because if you measure one mode and let's say 1 hour after you measure another mode and the system deviates after 1 hour, then you cannot really compare one mode to the other. So repeatability is definitely something needed. It's also important that the system is modulation independent, or at least has a flat frequency response. Because if it's not the case, it's very difficult to rank also the transmission modes. Like, for example, the LTE that may use a 16 QAM modulation and excite a bandwidth of 20 megahertz as a pretty different kind of spectrum as compared to a GSM modulation or type of transmission mode. And if you want to rank one mode with respect to the other, then the system has to be modulation independent, basically. And also, of course, when you want a good power meter, and that's how we use the system here, you want it to be linear. Otherwise, you cannot really measure anything. Just an example of the kind of test that we made with one antenna at the flat phantom of our system. It was radiating at 1920 megahertz, and you see on the top right part a figure showing linearity test where we decrease the power accepted by the antenna from 140 milliwatt down to 4 milliwatt, and you can see the SAR decreasing in an extremely linear fashion. So that's typically what you need from an array measurement system to be compliant with the key aspects that I just mentioned before. The bottom right figure shows the deviation of SAR with respect to the SAR when the antenna is fed with CW signal. And the different bars you see the antenna is fed with other kind of signals like EGPRS or different kind of LTE, FDD flavors, supposed to contain all the same power that we checked on the power meter, but you have to check that the device that measuring the SAR will see also the same power when measuring different kind of modulation. And what you can see from this graph is that the deviation from CW in terms of SAR result is no more than 3%, which is excellent to do the screening with the system. When using array systems, maybe some guidelines are good, like when you want to use them for screening. Because especially with the modern array systems, there are some nice automation features, like for example controlling the base station remotely to sweep through all the communication systems, bands, channels, modes, that can be used pretty efficiently. And in such a case, actually changing test position is usually the longest step. So it may be better to just fix one position and then go through all the modes, bands, channels first, instead of changing the position every now and then. Also, for devices using antenna tuner, it may be very interesting to have an internal software mode or an embedded software mode that allow to automatically cycle through the tuner states and eventually can be synchronized to the fast SAR system. That can be definitely pretty useful, but only mobile manufacturer can do that. Different procedures can be used for SAR screening. Well, the very basic one is the test everything procedure. It's very straightforward to understand. As we now have very fast SAR measurement system, very fast SAR tools, we can use them to basically measure every condition. So you position the DUT in a first test position, you make mid-channel measurement for all the communication systems that are covered by the DUT, then change the DUT position, and again go through all the communication systems until all the positions are tested, and you identify the worst case position and communication system, and for this condition you make low and high channel SAR test. And you may reproduce this highest condition identified with the legacy system. That would be a very, but also which basically is the least efficient because it's testing everything approach. Another kind of approach would be a more efficient and would imply some kind of test reduction, but based, let's say, on a smart procedure. I will give two kinds. This more or less is a very similar procedure, procedure 2 and procedure 3, but they have a different focus. Procedure 2 actually has a focus on communication system. And the idea of this procedure is to position the DUT in a first test position, then make mid-channel measurement for all communication systems, identify the worst case communication system in this position, then use this worst case communication system to test mid-channel for all remaining positions. And finally make low and high channel SAR test for the worst case position in communication system. Then in the end, this case would have to be reproduced I mean, the highest condition will have to be reproduced with the legacy system. Sorry. Well, using this kind of procedure, you save a lot of basically position communication system combinations. If some of you want to consult the black paper that we made, you will have a more detailed, let's say, evaluation on how many conditions you save using that procedure, which is still very conservative. Procedure 3 is more test position based. So it's more or less the same idea, but instead of focusing on the communication system as a pivotal point here, we focus on the test position. So you first select one communication system and you make mid-channel measurement for this communication system at all test positions. Then identify the worst case position. And after that, test middle channel at worst case position for all the remaining communication systems. Finally, when identifying the worst case position and communication system, you make low and high channel SAR test in this case. And you can reproduce again the highest condition identified with the legacy system. So that's basically another way to save a lot of conditions. For concluding this presentation, clearly the complexity of modern wireless devices makes it impossible to go through the SAR test matrix with traditional test approaches. So either test reduction or screening approaches that allow huge time saving really have to be used. But however, the user of the SAR measurement system or the antenna designer have to ensure that there is a conservative evaluation of the SAR for the given device. And for doing that, we propose some procedures and try to explain how they work. Basically, what you can see is that combining second generation of SAR measurement system that are based on amplitude and phase measurement together with screening procedures can result in very high productivity gains. Regarding regulatory acceptance for both screening and 6229-3 compliant array systems, I cannot say as of today that the sky is totally clear. However, it's already well advanced and definitely it shows the way to the future of EMF exposure conformity assessment. Thank you very much for your attention, and I guess there are a number of questions. So I'll be happy to take those questions. Thank you.
Great, thanks so much, Benoit. We'd like to have a call for final questions. Please enter any last questions you may have in the navigation pane. We've received quite a few inquiries on where to get additional information on this topic. There's a vast amount of content found on our website, emclive2015.com. You can also email us at info@interferencetechnology.com with specific needs, and we can direct you accordingly. Benoit, here's a question for you. You showed the relationship between conducted power and SAR. Can you please explain again why they are not exactly proportional?
Yeah, sure. Well, actually, there are two main things. One thing is, of course, you have uncertainty in measuring conductive power, and you have uncertainty in measuring SAR. That's the first point. Then the second point is when you measure conductive power, you measure it over 50 ohm. While when you're measuring SAR, well, first the RF transmitter of the device is connected to the antenna, which is not 50 ohm the whole way across the band. And second, the device is coupled with the phantom on which you are testing it. So you're not testing on a 50 ohm load in the case of SAR. So that's why there is not a perfect proportional relationship.
Great. We have another question from our audience. Do you have an uncertainty budget, and if so, is it releasable?
Sorry, I didn't hear.
Sorry. Do you have an uncertainty budget, and if so, is it releasable?
Yes, definitely. So our system as it complies with the typical 30% K=2 uncertainty requirement.
Great. You showed 3 procedures to SAR screening. One is basically test everything and the others simplify the test plan. Are 2 and 3 strictly equivalent?
Well, they more or less result in the same, they end up with the same results more or less, but they are not strictly equivalent. For example, the second procedure would be maybe more relevant in order, when you want to test like multiple transmission conditions, because as you get all the results of SAR in a given test position for all the communication systems, then you would have all the results you need to basically end up with the worst case condition, let's say, also taking into account the multiple transmission schemes. So I think procedure 2 would be probably preferable in a case where you have a, enabled simultaneous multi-frequency transmissions.
We have another question. How can the user verify that the tested signal is correct?
You mean, I'm not sure what exactly what's behind this question, but there are different ways to do that. Okay, one way is basically to have an external spectrum analyzer, for example, with an antenna plugged on it, and you can see what kind of signal you're measuring. But with our system, for example, we have this embedded function that we can really know what's the spectrum of the signal, so we can compare this spectrum of the signal to actually what's entered in the interface. Like if we say we're measuring WCDMA signal and it's not what the spectral contents looks like, then the system will know. Also, when the system is used for automating the base station control, the base station simulator, then our system would ensure that the SAR measurement system is synchronized more or less with what's entered in terms of parameters to the base station. So in this way, you would avoid to measure something while the transmitter is emitting in a different mode.
Great. We have one more question. What is the regulatory future of probe array technology, in your opinion?
Well, I think major regulators have been realizing that with modern wireless devices that may have so many possible transmission conditions, it's kind of getting really impossible to have a perfect coverage of all the test matrix and end up with a conservative SAR estimate if you don't introduce new procedures and new systems that can allow faster assessment. And I think we are moving in that direction that, if the regulators want a good coverage of the possible test conditions, they really have to authorize the new technologies like the array systems. So I believe it's the future of compliance testing, and I believe most of the regulators already realize that.
Great, thank you so much. We've received so many great questions we'll try to address in the future. Benoit, thank you again for your time and expertise. Please join us for EMC Live 2015 3-day event, which takes place April 28th to 30th. Webinar attendees, if you have any more questions we didn't answer here, please send us an email at info@interferencetechnology.com. A recording of this webinar will be available on our website, emclive2015.com. We will also send a link to all participants shortly. Thank you for attending.